Anyway, so I looked at our next unit. I'm happy. We're actually beginning true chemistry. Everything before this point has just been getting you ready. We're learning about ionic bonding. So, ionic bonding. What is an ionic bond? How do elements bond ionically? How will they react? So if we know which ones will react, forming ionic bonds, what are the equations? How will they react? What are their names? What are the names of the chemicals that are produced? Will two things react? Will they not react? If they do react, what do they make? So, little illustration. So perhaps one of you gentlemen wouldn't mind telling me what is outside the window you find so attractive? And we see that fluorine, chlorine, and bromine have negative charges, while sodium, potassium, lithium, and rubidium and cesium all have plus charges. This is ionic bonding, where we look at the ions and see how they react together. So a bond is a chemical force that holds atoms together and creates a compound with new properties which are different from the individual elements. Chemical bonds form because of the attraction between oppositely charged atoms called ions. Recall the octet rule. Atoms bind together or bond because they are trying to achieve a stable electron configuration like the noble gases. Besides helium and hydrogen, all the elements want 8. Hydrogen and helium only want 2. So every element is trying to get 8 valence electrons. I cannot stress that enough of how important the number 8 is. Except for hydrogen and helium that only want 2. There are 2 types of bonds, ionic and covalent, that we'll be looking at most in detail. And they differ in how that electron is given up in order to complete 8. In ionic bonding, the electron is completely given up. In covalent, it is shared. That's going to be the difference between an ionic bond and a covalent bond. So let's look at sodium and chlorine. Table salt, represented by the formula NaCl, is an example of a compound formed by an ionic bond. Sodium is a metal or not a metal? Is a metal. It's very metallic. It's on the left-hand side. How many valence electrons does it have? Y'all should always have a periodic table now from here on out. I cannot think of a day we're not going to need it. So how many valence electrons does sodium have? It's got 1. Its oxidation number is +1, or 1 plus. Oxidation number refers to the charge it'll have when it becomes an ion. That's not the proper definition. Let me Google the proper definition. What is an oxidation number? It describes the degree of oxidation of an atom in a chemical compound. Not very useful. Conceptually, the oxidation state or number may be positive. You can basically think of it as charge, but it's more fundamental than that. Because we can get integer values of charges. For ionic bonds, they're just going to be equivalent to the charge. So hypothetically, it's the charge the atom would have if all of its atoms, all the bonds are ionic. So oxidation number for this class, you can think of it as charge. It's technically more complicated than that, but because when we get to covalent bonds, we'll no longer be thinking about oxidation numbers, or we won't really cover the fractional ones. So you can just think of it as the charge you would have when it becomes an ion. So chlorine. Is chlorine a metal or non-metal? Non-metal. And how many valence electrons does it have? And what's its oxidation number or charge? 1 minus. So here is the example. Here's what's going on. So we have sodium and we have chlorine. Right now they're neutral elements. When they come together and form a compound, this is neutral. This is neutral. And when they come together, it's also neutral. So there is a 0 charge on this. And there's a 0 charge on this. There's a 0 charge on this. However, if we were to zoom in onto this, the reason they come together is because sodium is going to give its electron to chlorine. This makes sodium have a positive +1 charge and chlorine have a negative charge. But if we look at it as a whole, we know that the charge is equal to 0. So as a 0 charge in total, that means we have +1 plus a -1, and that's equal to 0. So +1 plus a -1 is a 0. So what's happening is, so sodium is, I've had to go over, we're going over chemistry and IPC now. I have to use like 100 periodic tables of me just writing all notes on them. So sodium is 3 and chlorine is also 3. What happens is this electron here moves over and gets on here. So now chlorine gets a slightly negative charge and sodium has a slightly positive charge. And if you remember what I stated about physics, is a positive charge and a negative charge attract each other. This positive charge is going to pull the negatively charged ion, chlorine, toward it, and the negatively charged chlorine is going to pull the sodium to itself. So the only reason these atoms stay next to each other is because chlorine is negatively charged and is going to pull on the positively charged ion of sodium. They attract each other because they have opposite charges. And this is why they stay next to each other. Is the fact that this electron has been given up and chlorine is holding on to it. And it now has a small charges, and these charges cause the atoms to continually push toward each other. The reason they don't ever fall into each other is because the electrons in the inner orbits, inner electrons, are being repelled. That's not right. So these negative electrons are being repelled by these negative ones, so it can only get so close before the repulsion of the two electrons pushes each other away. But overall, the net charge is positive on the sodium. That's the reason they stay together. That's all ionic bonding is. So what's some common ionic compounds? Sodium chloride, which is table salt used in foods. Sodium bicarbonate is a baking soda used in food, cleaning products, and antacid. Sodium hydroxide is lye, used in making soaps and drain cleaner. It's a base, the opposite of an atom, or opposite of an acid. Potassium nitrate is also known as saltpeter and is used in fertilizer, gunpowder, and food preservatives. These are all types of ionic compounds. You'll note some of them are polyatomic, meaning having more than two atoms. Just like some of the ions have more than two, are polyatomic ions. For example, in sodium bicarbonate, what are the ions involved? Let's look at that in detail. So, let's see if we can figure out some of this. So, sodium bicarbonate. What are the ions in the system? I will say this: an ionic compound has only two parts. They are very simple. They have an anion and a cation. That is the only thing. Anion is a negative ion, and the cation is the positive ion. Remember my mnemonic for remembering it. We draw a number line. We alphabetize it. Anion goes on the left because it's less than the cation, if we were to look at A and C. So that means if you alphabetize it, this is more negative, while this is more positive. So what is the anion and what is the cation of this element? And what are the charges on each of them? So go back to salt. Salt. What is the anion and what is the cation? Salt is composed of the cation, sodium, has a +1 charge, and chlorine, which is the anion, which is a negative charge. We know that this is a cation. So this is composed of sodium plus and HCO3 bicarbonate. What is the charge on this? What is it? So this is the cation, and this is the anion. What is the charge on this? What is the charge on HCO3? This is a compound. It is neutral charge. If we break it apart, we have a positive charge, and what must this be? Negative. Because +1 plus x equals 0. What must the x be? The only thing that makes sense is adding a -1 in for the X. So let's look at sodium hydroxide. What is the cation and anion? Should be very clear. Sodium is the cation. You'll notice that the ions of sodium is always the same. What about what's left? Must be anion. What is the charge of OH? -1. Potassium nitrate. You should know that everything in group 1 forms +1 and ions. So potassium is going to become a positive, it's your cation. And what's left has to be the other ion. So what's left is NO3. So that has to be your anion. And again, this is neutral, so balance the equation plus and minus. So this anion has a negative charge. Let's see if we can work through and this. And if I took magnesium and mixed it with chlorine, what do I get? How do these combine together? MgCl2. So what are the ions? The ions is Mg2 plus and chlorine minus. So our cation is magnesium, our anion is chlorine. But as you recognize, 2 minus 1 is not 0. This is a stable element. Anything that is stable has no charge. So in order to balance, we need to add 2 of them. So we need to make 2 of these for every 1 of these. Some other ones: magnesium sulfate, potassium bromide. So magnesium sulfate is known as Epsilon salt in the business. We don't use the chemical formula usually, unless you're in a science class. Most people just call it Epsilon salt. Potassium bromide is used to treat seizures in dogs. Sodium fluoride is an ingredient in toothpaste used for cavity prevention. Why do y'all think sodium fluoride is used? So fluorine is extremely reactive. Why would we want to put something in our mouth that will react with our teeth? Mm-hmm. So think about what I said about superacids. That one superacid. What was the only thing that could contain it? Teflon. Why was Teflon able to contain it? It's this long polymer. Because this acid, when it comes over here, this fluorine is already tightly bonded to the carbon. So the reason why you put sodium fluoride in your mouth, the fluorine is going to eat away on your teeth. So if we look at a tooth, the fluorine is going to come over here and eat away on your teeth. But whenever it eats away to your teeth, it's going to attach itself, and any food or germ that comes on is not going to have enough pulling power to pull that fluorine and break it apart. Does that make sense? So basically what you're doing is coating your teeth in a layer of fluorine. This fluorine is, so the bond between sodium and fluorine is not as strong as the bond between calcium and fluorine. So it comes up, we're putting NF and putting this, and it counters a calcium atom. This fluorine goes, nah, you're holding on to your electron too strongly. I'm just going to come over here and steal it from calcium. So it's going to break off and switch, and another fluorine is going to come over here and switch too. And now we have a very stable element or compound. And any food or germs that come over here is not going to be as strong as fluorine is. And so it's not going to be able to break the fluorine off your teeth, and your teeth isn't going to be able to decay. At least as easily as it still doesn't permanently prevent it. You constantly eating will scrape away the fluorine eventually. So calcium carbonate is found in rocks and limestone. So let's look at these two now. Do a little bit of analyzing. So magnesium sulfate. We know that magnesium is a 2+ ion. That means that sulfate is just going to have to be 2 negative, because there's only one of these for every one of these. The charges have to add together to be 0. Same thing for this, calcium carbonate. The ions involved is Ca2+, and carbonate is a -2 ion. So, ionic compounds are also known as salts. The word salt isn't used quite a bit, but if, like some formulas, like we usually don't think of baking soda or sodium bicarbonate as being a salt. It technically is. So this name is not often used, but if you ever see the word salt, that means it's a ionic compound. There's a single entity called the formula unit. This is the lowest unique. It's the lowest formula that describes the entire molecule. So you can see in this picture of salt on the top right, this unit of NaCl is actually bonded multiple times. It forms a crystal. So it's not just one NaCl and it's by itself. It's actually bonded over and over again. Every single chlorine is attached to 4 other sodiums and so forth, but we can break off one formula unit and that'd still be salt. Salts exist as solid at room temperature. I cannot think of any exceptions to that. They also dissolve easily in water. And they all exhibit a crystal structure, meaning that the formula units can bind with themselves and come stronger together. Again, you can think of it as the reason that in an ionic bond, It has a positive side and a negative side. All the positive side is going to attract any negative portion of all the other chemicals. So, they possess a very high melting and boiling point. So remember what it means to boil or melt. You have to overcome the attractive forces between the individual molecules. So when you're a solid, the individual molecules or the formula units all are pulled tightly together. When as you heat them up and they begin to melt, they're able to freely start moving and sliding past each other. Because a ionic compound has such a strong positive and negative side, it's really hard for another ionic compound to slide past it. So they really resist turning into liquids and gases because of how strong that pull is. They're also considered an electrolyte. This means that if you put an electrolyte or ionic compound into water, it enables the water to conduct electricity. And here's the key one. They have high electronegativity differences. So, is water an ionic compound? Is H2O an ionic compound? Why? So, remember, we did this already. We saw that peroxide, or no, hydroxide, so this is a hydroxide ion. Hydroxide ion has a charge of -1. And hydrogen before turns into a +1. They can combine together and make H2O. So is this ionic? Strongly no. You can think of it and apply some of the ionic rules to it, but let's look at what I just said. Ionic compounds are salts. They are solid at room temperature. They have very high melting points. So if we look at water, it does have a if we look at water, so according to this ionic thing, we should have a hydrogen that's positive, and we should have it attached to an OH that is negative. That is not what we see in water. We see each of these being positive, and the oxygen is negative. This is a covalent bond. This doesn't exist. We don't have an OH side and a single H on one side of the water molecule. So this is not ionic. We can tell it's not ionic because of the fact that we don't see this very strong differences. So looking at sodium, this side of it's going to be very positive. This side of it's going to be very negative. So let's put next to it another sodium chlorine. This is going to be very positive. So we're going to see a very strong pull between these two. This is going to be negative and positive. So we're going to see a very strong pull between these two. How easy is it to get this and this to slide past each other? it's going to be very difficult for these two molecules to actually move. Because there is a slight pull between the two molecules. This is why it forms a crystal structure, forms a lattice, where Na, Cl, Cl, Na, Cl, Na. We see the sodium bonding with chlorine. See sodium bonding with chlorine. Again, these two are bonding really strongly together. These two are bonding really strongly together, but there is a weak connection between them, which prevents them from bending. Water, on the other side, on the other hand, the electrons are shared, which means this is only very, very slightly negative, and these two are very, very slightly positive. On an ionic bond, this is a very, very strong positive charge, and this is a very strong negative charge. These are little tiny positive charges in retrospect. Water is not ionic. Again, you can tell this simply because of the fact it melts at 32 degrees Fahrenheit. Let me look up the temperature that sodium or salt melts. This is to give you a reference point on how high these temperatures is. 1,474 degrees Fahrenheit, or 800 degrees Celsius. You could put salt in a fire, it would not melt. You would need a very powerful blowtorch in order to melt it and turn it to a liquid. So extremely high melting points. So how can you tell if something will form an ionic bond? Let's go through this before I reveal the answer. Pull up your periodic table. I know this is wrong. Change this to a 2.0. And this should be an O. I have a better one. I have found it. I just need to reprint them off. So, let's look at sodium. And let's look at chlorine. What is the electronegativity of sodium? 0.9. What about chlorine? 3.0. So that's a difference of, the difference of En is 2.1. Let's look at magnesium chloride. Magnesium is, chlorine is still 3.0. So the difference in En is 1.8. We can't really do it with, let's see if I can find a value. OH electronegativity. Let's just do that. Let's just look at OH. So oxygen is 3.5. Hydrogen is 2.1. So the difference in En is only 1.4. This is not ionic. So what you'll see is that, remember that ionic compounds have a high electronegativity difference. Remember that everything exists on a spectrum. This is not an absolute fact, but generally we can classify anything above 1.7 difference as being ionic. So an ionic bond are composed of cations and ions bonded together. Atoms actually bond according to their differences in electronegativity, the ability to attract valence electrons, the ability of them to hold them when they're bonded together. If you look at a table of En values and find a difference between the two atoms involved, the absolute value, Subscripts don't affect it. Like in that example with chlorine, even though it has 2, you can ignore the fact there's 2 chlorine. We're just looking at comparing elements to elements. If you see that there is a difference between 1.7, it is ionic. So anytime you want to see if 2 things are going to react together, the first thing you should ask yourself, is the EN difference greater than 1.7? If it is, good. They're going to react and form an ionic compound. This is why we went over periodic trends. You should understand things on the left side of the periodic table are going to react with things on the right side. The closer they get together, the less likely they are going to react with each other. So we can see everything on the left has really low ionic or electronegativity, except for hydrogen. Everything on the right is very high. So calcium and arsenic. Do you think they'll react together and form an ionic bond? No. Calcium has an electronegativity of 1. Arsenic has an electronegativity of 2. That's only a difference of 1. They will not react together. So, lithium and chlorine. Lithium has 1. Chlorine has 3. The difference is 2. This is ionic. What about CO2? So, carbon has 2.5. Oxygen has 3.5. The difference is 1. This is not an ionic. That is a covalent bond to be specific. Magnesium oxide. 1.2 and 3.5. That's a difference of 2.3. That's ionic. As we work through these and practice more, you should gain the ability to look at the formula without looking at the periodic table and EM values and tell me if it's ionic based on just looking at it. You should know magnesium is far on the left and oxygen is far on the right. This means that it is most definitely an ionic compound. It's when you get to things that are closer together that you have to stop yourself and go, is this ionic? And for example, for this one, triboron diphosphide. Is that a ionic? You can tell that they're super close together. So they are very strongly covalent. You can also look at the formula and tell that the charges don't balance each other out. What's the charge on boron? +3. I take that back, they do balance each other out, but that's irrelevant because they're not ionic. This next one, NF3. Not ionic. Nitrogen has 3, fluorine has 4. The difference is 1, they are not ionic. So the formation of an ionic bond occurs when the valence electrons are transferred from one atom to another, usually between a metal and a nonmetal. Cations will donate, give, or lose electrons, and anions will accept, take, or gain electrons. The opposite charges make them attract together. This attraction is known as a bond. To give others by the electrostatic forces. So sodium normally has 1 electron on its valence, while chlorine is missing 1 electron. It's going to come together and donate it. The cation is going to give it away. The anion is going to receive it. Now there's a difference in charges, and those differences are going to pull them closer together. So the charge of the sodium ion is +1. Chlorine is -1. And the charge of the molecule is 0. Here's the important thing. The overall charge after they bonded together will be 0. That means it's stable, or that means stability. If you add up all the charges and it doesn't add up to 0, you've done something wrong. So let's assume that this is a ionic compound. Is this a true formula? Is this a correct formula? Could this possibly exist? No, the charge on the beryllium ion is +2. Charge on the nitrogen would be -3. So when we add these together, it's not equal to 0. Rubidium, bromide. Is that possible? So the charge on the rubidium is +1. Charge on the bromine is -1. But there's 2 of them, so that gets multiplied by 2. So the overall formula is +1 minus 2, which is not equal to 1. Or not equal to 0. What's the correct formula? RBBR. That's the correct formula. We have a +1, a -1 that cancel each other out. What would be the correct formula for this one if they, assuming they react ionically? 3, 2. We can see here, so this one has a 2 plus, has a 3 negative. But we see this gets multiplied by 3, this gets multiplied by 2, giving this side of the problem a total charge of +6, this side a total charge of -6, therefore a 0 net charge. I like also remembering this. The charge is going to indicate, so if we have a magnesium that is 2 plus, and a chlorine that is -1, when we write the formula together, this charge number is going to come over here and attach right here. This charge number is going to come over here. And then there's a final step. We don't put ones, and that's the formula. Let's do another one. Let's do magnesium and sulfur. So this has a 2 plus charge. This has a 2 minus. Write the formula beside them. 2 is going to come down over here. 2 is going to come down over here. But there's a final step. These both are divisible by 2, so we can reduce those as MgS. That's the formula. So for ionic compounds, we always use the formula unit. meaning that we always reduce it to the lowest numbers possible, and we omit ones. This is much later in the unit. I'm just filling the time since I got a minute or two. So what would be, here's a question for you guys. What would be the formula? What is the reaction equation for magnesium and chlorine? You don't need to know this now, but it's be useful later on to be thinking about it right now. So we know that magnesium 2 plus, chlorine minus, are going to react together to make magnesium chloride 2. So to show you how important this concept is to know right now, because after we do covalent, we're then going to do this equations like this. The answer to this is this. This is not the best example. You have to balance everything. So there's one magnesium on the left, one magnesium on the right. There's 2 here and 2 here. You have to know that this is diatomic. Best example would have been calcium plus chlorine should give you Cl like this. You should put a 2 here and a 2 here to balance it. But we'll pick this up on Monday.